All right, good evening, everybody. Welcome along to Café Scientifique. This is the last one of the academic year, so we will reconvene again in September, but this is it for the academic year. My name's Scott McIndoe. I am a prof in the Faculty of Science in the Department of Chemistry at the University of Victoria, and it is my very great pleasure tonight to welcome along Professor John Husson from the School of Earth and Ocean Sciences. John did his undergrad at Harvard, and then he did a PhD at Princeton, and then a postdoc at the University of Wisconsin in Madison. He studies the evolution of Earth's surface environment over geologic timescales, and in particular, he focuses on the interactions between the biosphere, climate, sea level, and ocean geochemistry. Tonight, he's going to be telling us about the Big Chill, global glaciation, and the rise of animal life. So a kind of climate change, but I guess in a different direction. So please join with me in welcoming John to the stage.
All right. Thanks so much, Scott, for the introduction and as well as the invitation to come and give a Café Sci. It's really a great honor. So yeah, we'll see how this goes. It's going to be my first time with a microphone doing a talk without any pictures to point to. So we'll you have to bear with me and yeah, we'll see how this goes. So yeah, so as Scott mentioned, I'm a sedimentary geologist. And I'm very interested in studying the history of Earth's surface environment, again, across geologic timescales. And so the reason that I study sediments is that sediments form at Earth's surface. And so because they do that, they record information about the chemistry, the biology, and the physics that's happening at Earth's surface when they form. And so the story I'm going to tell today is not truly my work. It's mostly the work of other scientists, people who have come before me and greatly inspired me, one of whom is in this audience. He's better qualified to give this talk than I am, so if I screw up too badly, he may pop up and correct me, so be on the lookout for that. So yeah, it's a story that I first learned when I was an undergraduate, and it's one that really inspired me to pursue geoscience, and so I hope you find it similarly inspiring as well. So I thought I would start the talk here by trying to contextualize, what I mean by geologic time and the age of the Earth. It's a tough concept to wrap your head around, even for me, even though I think about it literally every day of my life. So does anyone know how old the Earth is? Can I get a number from anyone? Yeah, I'm hearing 4.4, 4.5. Yeah, 4,500 million years old is a good age that we'll use for age of the Earth. That's when Earth formed. And so to try and put that into some sort of context, I've laid out a measuring tape, 10 feet. Sorry, it's an American measuring tape, so forgive me. So we're dealing with feet. But 10 feet is supposed to represent 4,500 million years ago. So Earth formed over here at this chair, and then our present day, where we're all sitting enjoying a nice evening together, is over here at this chair. 4,500 million years later. So I'm going to walk through and mark off some important events on this geologic timescale. So if I move to, let's see, I've just written this down. At this point here, where the front toe is, this is when the oldest sediments that we know of formed. So at a place called Ishua, Greenland, 3,800 million years ago. And so from my toe forward, we have sedimentary rocks that are recording some part of the timescale thereafter. So it's a big event. It's an important archive because, as I said, that is what we use to learn about the evolution of the surface environment. So now let's walk a bit more further in time here, about almost halfway through. Again, my foot is marking about 66 inches. This is 2,500 million years ago. And this is when oxygen first appeared in Earth's atmosphere. So behind me here, to that chair over there was no oxygen in the atmosphere. After this time and forward, there's at least some. at this point, we couldn't all take a deep breath. There wasn't enough oxygen to support animal life. It was about, say, 1% of our current levels, but there was some measurable amounts, and oxygen remained in the atmosphere ever since then here. So let's walk forward still more to about 19 inches, 720 million years ago. This is when one of these very severe glaciations happened that I'm going to be talking about today here. And so you can see, even though it's 720 million years ago, that's a long time ago, it's quite close, it's much closer to our time than the formation of the Earth, just to give you a sense of how immense geologic time really is here. So if I inch, pardon my pun, my foot a little bit forward to 14, that's 14 inches, that's 520 million years ago. This is when animal life that's broadly recognizable appeared. And what I mean by that is the major groupings of animals, the phyla, which are the sort of the largest category of animals that you can think about, those all appeared essentially in a geologic instant in what's known as the Cambrian explosion. And it's called an explosion because of this sudden appearance, to a geologist at least, happened within the rock record here. So I move my foot back to where that first glaciation was, here to here, they're very close to one another. That's provocative in terms of thinking about a connection between the evolution of the environment, these glaciations, and animals here. So from my foot to this chair, that's the age of animals, the Phanerozoic eon, it's called. And so to put humans on this time scale is actually really a challenging thing. So the smallest gradation that this measure has is about 1/16 of an inch. And that's when humans, at least the oldest species of humans, arose in that final 1/16 of an inch at the very, very end of my time measure there. And that's not even modern humans. It's just the oldest species of Homo, our genus, Homo habilis. So if I wanted to give human species, Homo sapiens that is, about 10 centimeters of distance, I would need a tape measure that's 1.5 kilometers long to accommodate the rest of the history of the planet. So if you think about the history of Earth, humans are not a part of it for the vast, vast majority of it, even though they are, of course, a dominant force today in terms of shaping our environment. That is not the case for what I think of as Earth history. So so as I said, the story I'm going to be telling is one, again, the work of other scientists. And I want to bring in arguably the most famous natural scientists of all time in terms of relating back to, again, the geologic timescale and events therein. And I'm speaking of Charles Darwin. And so what Darwin knew at the time, let's go back to 14 inches, the appearance of the major animal groupings, the Cambrian explosion. What Darwin knew about, he didn't know how old the Earth was, but he did know that there were essentially no animals for a vast stretch of the record. And then in a geologic instant, all the animals, the major groupings at least, had appeared and were there and were present from thereafter. And so this greatly troubled Darwin. He thought that the record did not support the ideas he was developing for natural selection as the origin of species. Because Darwin was a gradualist. He believed in small changes from species to species should take place, and sort of greater complexity developing along the way. And so the record of no animals to all the animals was one that was very, very disturbing to him. And so I'm going to read some quotes from Darwin, because he's a much more poetic writer than I'll ever be, and to sort of how him grappling with this idea here. So there is an allied difficulty, which is much graver. I allude to the manner in which numbers of species of the same group suddenly appear in the fossil record. So this is the Cambrian explosion. The case must at present remain inexplicable and may truly be urged as a valid argument against the views herein entertained. So Darwin went on, if my theory be true, it is indisputable that before the lowest Silurian stratum, and so in his times, he meant that's the word for Cambrian in terms of the first appearance of animal life that he knew about. But before the lowest Silurian stratum was deposited, long periods elapsed, as long as, or probably far longer than, the whole interval from the Silurian to the present day. And that during these vast yet quite unknown periods of time, the world swarmed with living creatures. So this is Darwin's idea, his conception of what majority of Earth history must have been like, but just not preserved for him to see. And so probably his most famous statement then about the rock record that actually exists today comes from chapter 9 in his book on the origin of species. And so he writes, "I look at the natural geologic record as a history of the world imperfectly kept and written in a changing dialect. Of this history, we possess the last volume alone, relating only to 2 or 3 countries. Of this volume, only here and there a short chapter has been preserved, and of each page, only here and there a few lines." And so in other words, I've laid out a continuous tape measure depicting the history of the Earth. So in Darwin's view, what I would need to do then is chop it up and basically get rid of much of what's going on back here in the deepest part of Earth history and get more and more bits as I march forward in time. This is what he thought needed to be true, and if his ideas of natural selection were correct. So it's if you sort of think about sort of Darwin's reaction to it, the record is what it is, and probably what it's pointing to is the ideas of gradualism. His conception of how evolution proceeded may not be as correct as it actually proceeds. So. Knowledge in general of geoscience, has improved since Darwin's day. And so, for example, what may allay Darwin's fears a bit, if we go back to 2,500 million years ago, that time period when oxygen first appeared, from that point onwards and a bit before as well, there's a record of microfossils that indicates the presence of life. So microbial life was present and doing things like producing oxygen. And so that sort of speaks to a much longer record of life than Darwin knew about. And moving forward to the animals, again here at 14 inches, we now extend the record of animal life, a bit past the middle of my foot too. So we could push back a bit the record in which animals exist. Maybe not enough to allay Darwin's fears, but that is certainly the case here. And it's roughly, again, in that window around my right foot here are the events that I'm going to be talking about for the rest of my talk. These great climate disasters of global glaciation here. And so because I'm going to be talking about climate, it's helpful to start with a discussion of, how or why does Earth have a nice climate to begin with? One that is amenable and can support a biosphere, all of us. And so, for example, let's think about our nearest planetary neighbors. I heard someone use the word Goldilocks, which is a great way to be thinking about this problem. So if we look at Venus, that's our neighbor, our planetary neighbor closest to the sun compared to us. It has a surface temperature of around plus 464 degrees Celsius. So very, very toasty. Too toasty for life, or oceans, or liquid water. So that's our neighbor closest to the sun. Let's look to Mars. Average temperature of Mars, minus 60 degrees Celsius. So far too cold for liquid water or oceans. And so based on how I presented that, in terms of comparing closer to and farther from the sun, distance from the sun is a really important variable here for sure. And that's because the amount of solar energy that any planet receives is controlled very directly by the distance from the sun. And so every planet is receiving that energy based on its distance. Although some of the energy every planet receives is just simply reflected back into space. So it's never absorbed to heat up the planet's surface here. And so this is a parameter that's called albedo, which relates to basically how shiny or reflective surfaces. So for example, I've got two sweatshirts here, courtesy of my kids. So I got one that looks like this, and one that looks like this. So let me try to do some microphone manager here. So yes, here we go. Okay. So I got two sweatshirts, this one and this one here. So which one would you wear if you wanted to be warmer? The black one. See, all of us here, we're always doing energy balance calculations in our head when we pick what we're going to wear for the day, right? So this is an exact demonstration of what albedo is. The darker colors have a lower albedo, meaning that they're absorbing most of the energy that's being shined upon them. And lighter colors, white, has a higher albedo, which just means that a greater percentage of that energy is simply being reflected back out into space here. And if we think about the Earth's albedo, a good number for that is about 30%. So 30% of the incoming solar energy is simply reflected back out into space. And for any energy that is absorbed by a planet, any planet, including Earth, that incoming energy needs to be balanced by outgoing energy. It's going to be emitting energy that's different from what it received, but it needs to balance. There is no running of any deficits or surpluses when it comes to energy received from the sun. So, that is the concept of energy balance, which is a great way to predict, at least at a first order, what a planetary surface temperature should be. So again, given this assumption of energy in is equal to energy out, you can calculate what Earth's surface temperature should be. And let's assume for the moment that there's no atmosphere. So when I do that calculation, I get a number of minus 18 degrees Celsius. So too cold for liquid oceans. So what's the problem here? What am I missing? Yeah, the atmosphere. What's specifically in the atmosphere? Clouds, that's part of it. Greenhouse gases, yeah, that's another important part. So greenhouse gases such as CO2 is a really important part of the equation here. So Earth still needs to obey this law of energy in equals energy out, but the presence of greenhouse gases in our atmosphere, such as CO2, changes how that energy balance is achieved and allows the surface temperature to be higher. So if I add a very simple representation of an atmosphere with greenhouse gases in it to my energy balance model, I get a surface temperature, again, just based upon the amount of energy we're receiving from the sun, of around plus 15 degrees Celsius, which is not a bad average pre-industrial temperature to calculate, to use there. So it's the presence of greenhouse gases given today's input from the sun that allows liquid water to exist. And so I want to pause here and make it absolutely clear so that I'm not misunderstood. The lowering of greenhouse gases in our atmosphere is a really important project, one that I wholeheartedly support. So I don't want anyone to think, oh, this is going to threaten a global freeze or anything like that. It's still a really important thing to do, given the effects of anthropogenic global warming. But if you think again in geologic timescales and the scale of Earth history, you should certainly think about the presence of greenhouse gases as guaranteeing liquid water in the pre-industrial age. Okay. So that's the present day atmosphere and the present day surface temperature. What about if we think about the climate in Earth's past? Let's go back to those first sedimentary rocks, which are around here. We have to think about how our sun has evolved over the course of Earth history. So today, as when it formed, the source of solar energy are nuclear reactions happening inside the sun. Hydrogen, atoms of hydrogen are being fused together to make helium. And when that fusion reaction happens, mass is lost. And that mass that's lost is being converted into energy. And you can use Einstein's equation, E equals mc squared, to calculate what that energy creation is. So m there is the loss of mass, how much lighter helium is than hydrogen per unit per atom. And C is the the speed of light. So I always feel cool whenever we use Einstein's equation, so I try to do it as often as possible. And that means that that is the source of energy that's being emitted throughout the solar system. Okay, so those, as I said, those reactions started over here when the sun formed along with the other planets in the solar system. But the rates of those reactions have been speeding up throughout the sun's history. So what that means in the past is that the sun was dimmer than it is today, and it's been brightening ever since as the sun ages here. You could put a number to it actually, so that our sun was about 30% dimmer when it formed than it is today. And if you think about, again, our ischius sediments, our oldest sediments in the record here, the sun was about 25% dimmer. At that time period, if we think that Earth had an atmosphere like it did today, Earth should be frozen. And that is a problem to reconcile with the presence of sediments, because sediments require liquid water. So we have an issue here where even with, we consider the amount of CO2 that exists today, it's not enough to have Earth be warm with a liquid ocean at this time period here. So this is really an excellent example of, say, a contrast between a theory, a prediction from theory, and what the observations, the empirical observations, are telling us here. And so we have sediments, at 3,800 million years ago, and sediments throughout the time period afterwards here. And so there's something is missing. So what is a solution to what's known as the faint young sun paradox, which is how do we have sediments in the presence of a dimmer, less energetic sun? What do we need? What do we need to have that be the case? Yeah, exactly right. So more greenhouse gases is a prediction for how to solve the faint young sun paradox, such as CO2 gas. Okay, so this is great. We have a hypothesis that greenhouse gases must have been higher here where I'm standing in order to allow things like the ischius sediments to form here. And I'll go further and say that every indication from the record as I march forward through here is that Earth has had a relatively stable temperature with some, of course, notable exceptions, which we'll get to in a moment here. Let's say that the temperature range of the Earth as I'm walking through time here was about +10 to +35 degrees Celsius. Those numbers are somewhat arbitrary. It's just meant to show you that they're stable and always allows for basically liquid oceans to be present here. But then let's think about what that means. So as we start here, when we say we have higher greenhouse gas concentrations to allow for the ischius sediments to form, if I take a step forward like this, what's going to happen to our sun? It's going to get brighter. But if we want a stable climate to stay in that range, that relatively narrow range that I said, what needs then to happen to the CO2 gas, to greenhouse gases in the atmosphere? It needs to be reduced. And if I step forward again, that needs to happen again and again and again as I'm marching forward. So there needs to be some mechanism, something natural within the Earth system that regulates the amount of CO2 in the atmosphere. And so the late, great oceanographer named Wally Broecker liked to say that there must be a climate policeman, someone to keep climate in check, specifically CO2 gas concentrations, if you want to think about it that way, in check as the sun gradually brightens from its original state to where it is today here. And so the idea proposed for that policeman, for what's doing that regulation, is erosion and the creation of sedimentary rocks. And specifically what I'm talking about is a kind of erosion called chemical weathering, where I'm taking minerals from igneous rocks. So this is a bit of polished countertop that's made out of granite, and there's beautiful interlocking crystals of things like potassium, of minerals such as potassium feldspar. And when chemical weathering happens on igneous rocks such as this, you're transforming the individual minerals in there. You're making them into something different. And so what you're creating, or rather what happens with chemical weathering, is you're using carbon dioxide, dissolving it into water, and that makes carbonic acid. And that carbonic acid is reacting with minerals in igneous rocks, and it's producing two things from those minerals. One, it's producing dissolved metal ions, like calcium. And two, it's transforming the original solid, the mineral, potassium feldspar as example, into a clay, into a soft clay that you can find at the beach. You go to beaches around Victoria, maybe you guys know, if you dig down a bit at certain areas, you'll get to a beautiful layer called the Victoria clay layer. Those are the products of chemical weathering, the transformation of feldspars and the like in igneous rocks here. So what happens next? Well, the calcium, the dissolved carbon, the carbonic acid that came from rainfall, and those clays are all washed away into the oceans. Okay? And then finally what happens after we get into a marine environment is the calcium ions and that dissolved carbon, they combine together to make a sedimentary rock called calcium carbonate. I have a sample of it here. So, and this is, these are full of round forms called ooids, but they started off their lives as a salt that precipitated directly from seawater. So calcium and dissolved carbon combined to form calcium carbonate. So that's one kind of rock that you form as a result of chemical weathering. The other kind of rock you form, at least in a very simplistic sense, is what happens to those clays. And you get things like shales. So compressed clay will make mudstones and shales. This has also lots of organic carbon within it too. And they become part of the sedimentary rock record. So the net result then is that we took an igneous rock, my countertop, and we created two different kinds of rocks as a result of that, a shale and a calcium carbonate or limestone here. And along the way, what happened is we took a CO2 molecule, or rather lots of CO2 molecules that were in the atmosphere, and we locked them up into sedimentary rocks. So that those CO2 molecules are no longer in the atmosphere. They're now in rocks. And by the way, this is a method being developed to try and ameliorate the amount of CO2 gas that's in our atmosphere today because of anthropogenic activities, basically accelerated chemical weathering, turning it into solid rock. And there's all sorts of different test projects around the world trying to do just that. And let's get back. We get back to nature and how it operates there. This is really nature's way of removing carbon dioxide that gets into the atmosphere, and we refer to it as the geologic carbon cycle. And so the way to think about it, in its simplest sense, is that volcanoes all around the world, such as Mount Baker that looms over Victoria, we can all see it on a nice day, that volcano and all of its partners, in both on land and in the oceans, are emitting CO2 gas to the atmosphere. And this process of chemical weathering then draws down those CO2 gas molecules, such that if we think about rates of volcanic outgassing from CO2, if those are equal to rates of chemical weathering and carbonate burial, there's other ways of burying carbon. Let's just focus on carbonate burial. That means that we can have a steady amount of CO2 in the atmosphere. We're not going up, we're not going down. It's just steady, just like our previous ideas of energy mass balance. No deficits, no surplus. It's just going to be the amount of mass and of CO2 in the atmosphere is going to be unchanging with time here. So what's amazing about this system is that it self-regulates. So what I mean by that is it's important to realize that chemical weathering is a chemical reaction, and as implied by the name. And chemical reactions, a feature of them, is that they run faster at higher temperatures. So if we have a thought experiment where let's say volcanoes are especially vigorous for a set period of time, more CO2 gas is being pumped into the atmosphere. So what happens to global temperatures? They rise. What happens to chemical weathering rates and carbonate burial rates? They also go up, and we go back to our original forcing. CO2, the amount of CO2 is then drawn down by those accelerated rates of chemical weathering and carbonate burial. And so it's a beautiful feedback, a negative feedback. Negative here means not in the sense of bad, but in the sense of resisting change that was originally forced upon it. So the original forcing was I made CO2 go up with my vigorous volcanoes, and then the system fought back and sought to restore the system back to its original state of lower CO2. And so you can now think about, again, in the context of the faint young sun and its brightening nature. So as we march forward in time, the sun is brightening, and temperature is going up. Temperatures go up, weathering rates go up, carbonate burial rates go up, draws down CO2 and allows you to drop global temperatures. So it's a way to to allow Earth to be have a stable temperature in the face of this changing boundary condition, which is a brighter and brighter sun. This is called the silicate weathering feedback. And it's proposed as being the climate's policeman. That is what is regulating things to keep us within a relatively narrow range of global temperatures. And so this idea for a planetary thermostat has been called an idea too good to be wrong, which is a great way of putting it, not necessarily scientific, so being a bit facetious there. So you can always be wrong in science, but what I would say is that this is a really very elegant hypothesis, an idea with a lot to support it from the geologic record here. Okay, but has it ever failed? Has this climate regulating mechanism ever failed Earth and allowed temperatures to go out of this sort of habitable range? And the answer that yes, it may have, first came to the scientific community by way of early climate models. And these models were developed, or rather their first uses were developed to try and explain how we got the last glacial maximum. So when ice sheets were larger 26,000 years ago, so they covered all of Canada, much of Northern Europe, Siberia, Antarctic ice sheets were also larger. This again happened 26,000 years ago. And so these early climate models were trying to see, what amount of cooling, because it was found you needed to cool the planet a bit, lower, say, the amount of CO2, to allow those ice sheets to grow. They accomplished that feat, but they discovered something funny about the climate system if ice sheets grew too big. So let's again think about what's going to happen as we grow an ice sheet. So the area covered by ice is going to expand, right? And so what we're doing, if we go back to our sweatshirts, right? So we have darker land, like our black sweatshirt, being covered up by ice, which is essentially white, much higher albedo. Okay, so what happens then, once albedo increases, is more energy is now being reflected back out into space. And that does what to global temperature? Makes it go down. So temperatures now have gone down. And so what then may we do to our ice sheets? Encourage them to grow, which will do what to our albedo? Increase, and down goes the temperature, larger go the ice sheets, so on and so forth, in a feedback loop that is not negative, it's positive, meaning that initial change we introduced to the system, growing our ice sheets, caused the system amplified that, such that if ice sheets get too big, if they creep past too much of down from their polar positions towards the equator, they become unstoppable. Again, this is all in climate models, right? And they cover the Earth. And this is known as the ice albedo runaway feedback. Okay, and so it's a way to cover a planet in ice, at least predicted by models. And so, has the ice albedo runaway ever happened on Earth? So to answer that question, you need to again look at the observations. And this is where the work of field geologists working all around the world becomes extremely vital and important. And what people have found in sediments that are about 720 million years old is that there was evidence for the presence of past glaciers. Okay, And the type of sediments that these field geologists were documenting came in two different types, or at least two types that I want to highlight to you tonight. The first were called tillites. And so there's lots of glacial till on Vancouver Island. This is a tillite where it's been lithified. And I don't know how well it is you can see, but it has these pink chunks, which are coming from, I don't know, let me try and do this. I'm used to having like all my hands, so. Anyway, so this tillite is composed of these clasts of pink rock, which came from the erosive power of a glacier moving over land. And that's one part of the rock. The other part is this green, very, very fine-grained rock flour in between. So this whole rock came from the erosive power of a glacier or an ice sheet on land, grinding up the bedrock, making this slurry, this mixture of very, very, very fine-grained sediment, the green, and the coarser-grained stuff, the pink, and just transporting it all together and dumping it out in a big mess called a glacial till, or rather a till or a glacial dimictite. So this is evidence of a glacier on land, or ice sheet on land. So that's the one type of glacial sedimentary rock that's been documented. The second kind looks like this, where we've now left land and we're looking at sediments that formed in offshore marine environments. And so where you get quiet deposition of, say, mud and silt that's being transported by, say, rivers, and you're making these beautiful laminations. So just tiny, tiny layers of sediments accumulating different colors, make pretty striped patterns in those sediments. But disrupting that depositional process in this rock is a pebble that looks like it got shot straight downward from above. That's exactly what happened. There was an iceberg overhead having lots of sediment in its bottom and melted out and dropped these projectiles downward in this ice rafted debris, disturbing that marine sedimentation below. And so when you find tillite in the same place as ice rafted debris, it's telling you that there was an ice sheet or a glacier that made it all the way to sea level and was sending off icebergs into the ocean where you were creating this ice rafted debris. You need both to be able to say that. If you just have one, you can't say it that an ice sheet was present in the area you're observing. So those glacial units, that evidence of glacial sedimentation, is found on all continents, except for Antarctica, which is ironic. But everywhere else, North America, South America, Asia, Africa, Australia, Europe, they're found. Okay, so it's appeared to be a global event. Again, with all in sediments that are dated to be the same age. And so some of those continents may not be that surprising. So for example, ice sheets on Canada, that's not that unusual. It happened 26,000 years ago. But you have to remember that continental blocks don't stay in one place across geologic time. They wander due to plate tectonics. And so the real kicker with this glacial sedimentary evidence is that if you interpret where those blocks were when they formed, many of them formed at the equator. Or rather, they were at the equator when those glacial sedimentary units formed. And so now you've got ice sheets and glaciers at sea level at the equator. And that is a very much unlike any ice age or glaciation that's happened, certainly within the last 500 million years. We've had ice ages, we've had expansion of ice sheets, some quite large, nothing like this where those ice sheets made it all the way down to the equator. And so the idea is that if you have ice sheets at the equator, that implies that the areas north of the equator towards the poles must also have been frozen as well. So temperate latitudes, polar latitudes, sea and land frozen. This is really the central claim, rather, or rather what I see as the central component of this Snowball Earth hypothesis, this presence of ice sheets making it all the way to sea level, again at the equator here. And so the Snowball Earth climate state, if you will, this state of a frozen Earth, would actually have been a very, very stable climate because albedo would have been extremely high. This is what Earth would have looked like from space. And most of the solar energy, even if it's increasing with time, would have simply been reflected back to space. So very hard to keep, get the surface temperature warmed up at all because of that high albedo. And so these types of severe glaciations may have not happened just once, but in fact twice in rather close succession. So it's 720 million years ago, as I said, evidence of this occurred, ice sheets all the way down to the equator. Earth escaped from that climate state, and then 650 million years ago, it fell into it again. And another Snowball Earth glaciation took place. And if you think about, if we go back to around 2,500 million years ago, so that's about here, and look forward, there are just these two events that appear to fit the bill of these severe global glaciations. So as I said, quite unique and quite an unusual climate state that Earth found itself in. So then how did Earth then escape this frozen state that it found itself in here? So if we now go to another thought experiment and we think about Earth being locked up with ice, what are going to be rates of, say, chemical weathering in this world of ice sheets from pole to the equator? Very slow or zero, yes, because temperatures were frozen. You're not going to have much liquid water running over land to erode or rather dissolve rocks like we do have today here. And so that is the prediction of what things would be like in a Snowball Earth state, However, volcanoes, they're not going to stop putting out their CO2. They do not care one way or the other whether the surface is ice-free or ice-filled. The CO2 is coming out of the solid Earth and it's going to make it into the atmosphere. And so if you got millions of years to spare, like we do when we're thinking about Earth history, that CO2 gas is going to make it into the atmosphere and it's not going anywhere. It's just going to sit there because chemical weathering rates are zero and it's not going to be turned into rock. So wait millions of years, CO2 gas will build and build and build and build. Eventually, the greenhouse gas forcing from so much CO2 in the atmosphere will be enough to overcome that high albedo state and melt back all the glaciers and deglaciate the planet here. And so this is really a central prediction from the Snowball Earth hypothesis, is that if you're in a Snowball Earth glaciation, it should not be a short affair. It should last millions of years. And that's because the escape is tied to that solid Earth degassing from volcanoes. That is how you get enough warming to escape from that frozen state. So if you say, oh, well, I think this interval of time is a Snowball Earth episode, and you figure out how long it lasted 500,000 years, probably not a Snowball Earth. You don't have enough time to accumulate enough CO2 gas in the atmosphere to escape. So that's what's one of the beauties of the idea, is that it's a hypothesis that's providing distinct predictions that you can go out and test with observations from the rock record here. Okay, so once those ice sheets are gone, Earth is going to find itself in a hellish greenhouse gas state where CO2 levels are extremely high, and now the planet is no longer white and shiny, it's dark and absorbing lots of that incoming solar radiation. So temperatures are going to be extremely high. And so in a post-snowball world, the erosion rates and the chemical weathering rates are going to be extremely high. One, because of just the high levels of CO2 gas, the high temperatures that Earth is experiencing. And two, because glaciers have just spent the last several million years or more grinding up that bedrock into this rock flour which is going to be extremely reactive with any kind of acid you throw at it. And so the prediction is that chemical weathering rates are going to be extremely high, and they're going to be pulling that CO2 gas from the atmosphere, dumping it into the ocean as dissolved carbon, as well as those dissolved calcium ions and other ions that come along with the weathering of igneous minerals. And the prediction is that you're going to be then wanting to precipitate and dump out lots of calcium carbonate that comes along from those processes here. So for a demo here, I'm going to try to do a Snowball Earth episode in a beaker here. So let's see how it works. Safety first here, some safety goggles. Okay, this is supposed to represent the glacial tillite rather, that formed. So just a bunch of stones and pebbles at the bottom of my beaker here. So let's now add some calcium ions in solution here. There's calcium. Yep. This is supposed to represent those high weathering rates. It's going to be dumping these cations into the ocean here. And as I said, it's going to be pulling lots of carbon along with those cations as well into the oceans here. And so this is now the carbon coming in as well. And it's turning milky white because calcium carbonate is precipitating out from that solution, which is going to be super saturated with respect to that particular mineral, that particular salt, and precipitating out. And so it's going to take a while to settle, but if we wait long enough, what we're going to see is a layer of glacial rocks at the bottom, and then sitting on top of that, draping those glacial rocks, are going to be my calcium carbonate rocks. So you're going to have a cap of calcium carbonate sitting on glacial units. And so those are referred to as cap carbonates because they're sitting on, they're capping rather, the glacial units observed. And it's bubbling because it has this reaction produces CO2 gas, which is being outgassed from our beaker here. So it's making a nice frothy mess, but it will settle down, and hopefully again we'll be able to see a layer of white on top of our tillite at the bottom of our beaker here. So to go back to Snowball Earth hypothesis here, that's another prediction, which is that you should transition from a glacial state, frozen Earth, to a hothouse, greenhouse state, more or less instantaneously, certainly geologically speaking. And when you do that, you're going to stop depositing glacial sediments, those tillites, and you're going to actually deposit these cap carbonates on top of it because of this high CO2 atmosphere that's being scrubbed out by extremely high rates of chemical weathering, which are going to be working in overdrive to get rid of all that excess carbon that's been hanging around in the atmosphere for millions of years, where it should have been buried long ago if Earth was operating more normally. So that's a prediction, and it's observed. In those two sets, those two Snowball Earth episodes, you've got glacial units, duration millions of years. On top of that, carbonates. And that pattern is observed everywhere around the world that these units are observed. So that's for the older glaciation, the one about 720, and for the younger glaciation as well, the one that initiated between 650 and 645 and ended around 635 million years ago. So again, we now have a second prediction that we've talked about that is being supported and consistent with the rock record as we observe it. Okay, so let's see here. All right, so I'm over time here, so I'm actually going to just wrap things up a bit and open it up for more questions. So Snowball Earth, I think, is a really excellent example. Sorry, the Snowball Earth hypothesis is a really excellent example of how the scientific process works, or rather should work, in Earth science here. So it's really an amazing hypothesis because it involves contributions from many different disciplines, sub-disciplines, if you will. So we talked about climate physics, talked about field geology and sedimentology, geochemistry. All of that is at play when trying to think about and test predictions that come from the Snowball Earth hypothesis here. And making testable predictions is what it's all about. If you can't make something that's testable, you can't go out to the field and measure something that would either disprove or support that hypothesis. It's not really moving things forward as it should here. And so scientists are still debating today. What were the what was the nature of these global glaciations in more sort of fine detail, and what were their consequences? And that includes try to bring things back to animals. I sort of didn't talk about them as much as I had planned to, but again, this close temporal connection between the ending of these Snowball Earth episodes and the rise of animal life, which is at least temporally close and may have sort of a causal connection, which is still being debated today. So I'm going to stop talking now, and I'll hand things over, I guess, to Scott for Q&A here. Thank you very much.
Thank you so much, John. I love seeing a bit of live chemistry. Any questions for John?
I have one.
Yes, please.
I have
30 questions. Maybe just one.
It's probably geology 101, but I interpreted the amount of water that was present on the Earth during the Precambrian and basically continents. I'm not sure how plate tectonics worked in, like how widespread were continents to produce the sedimentation that you're dealing with.
So the question is, how widespread were the continents way back in the Precambrian to produce the sediments you're talking about today?
That's a great question. It's certainly those types of questions are definitely actively being researched today in terms of what was the growth of continental crust like, and people have made different curves for how much continental crust has, and how that's accumulated through time. Certainly by the time period we're talking about, 720 million years ago, there were many different distinct crustal blocks that were called cratons, and they have been stabilized for and around for, at this time period, almost 1 billion years. And so we can track at least the movements of these blocks of crust through time, and those would have been around, present, moving around, producing sediment via erosion and the like here. Certainly, the deeper back you go, it's an open question about, one, when did plate tectonics start in the modern style we know it today? And two, when did continents first start to grow and emerge from under the sea? But when we're talking about now, you can more or less think about blocks and plate tectonics as operating as they are today.
And the source of water is what?
The water, well, so ultimately the water is coming from, it was present. That's a good question. Why Earth has as much water as it does? It's actually not an obvious answer to that question. But certainly the idea is that it had that amount of water when Earth formed. Now, it could have moved around from, say, the mantle and the hydrosphere through things like subduction and volcanoes, moving those volatiles around. So it's not an easy, you can't really answer that question very well about what was the mass of ocean water, or at least I can't think of an answer to that off the top of my head. How to constrain the mass of ocean water, in these time periods and when it's forming here. So, yeah.
Thank you.
Yes, in the middle there.
You mentioned all kinds of regulation there, but nothing to do with biological regulation. So I'm wondering, to what extent did living systems
So the question's about biological regulation of the climate.
An excellent question again. So one way that biosphere is involved very much in climate regulation is I mentioned burial of carbon via calcium carbonate burial. That accounts for about 80% of outgoing carbon going today. The other 20% is from organic carbon. And so that, of course, absolutely requires a biosphere to be around to produce that carbon. Now, the carbon you produce in the biosphere, most of that is just going to be respired away and never make it into buried sediments here. And so, but about if you think again about the amount of carbon leaving the system, about 20% is doing it as organic carbon. Now, the role that the biosphere plays in regulating, say say sort of a stable climate or a habitable one, that actually has a name. It's called the Gaia hypothesis. And the idea is that the evolution of life is actually part of the stabilizing force that keeps Earth within a certain bounds that are sort of amenable to life itself here. So that's again an idea that's out there that in fact life it's not as simple as saying the inorganic systems allow life to arise. It's that the life systems themselves maintain a planet that's habitable to life itself here.
I think there's a question over here. Yes, please.
Yeah, years ago, 50 years ago, when I was dabbling in this stuff at university, this was just unheard of. The precursors for glaciation back then were things like the Chandler wobble and the Milankovitch theory. Have those things just been dispelled now, or is there still room for those in the discussions?
Can you tell us a bit about some of the older theories and to what degree they've been dispelled?
Great question. So Milankovitch cycles are still very much a part of how people think about glacial, interglacial cycles. And so if you study, say, glaciations, so I guess maybe I should step back. The Milankovitch cycles are the idea that Earth's orbit changes in very predictable and predictable ways with predictable time periods. And so there's three main cycles that you could think about that are changed at these regular beats. The first is eccentricity. So that's how oval versus circular Earth's orbit around the sun gets. And that changes every 100,000 years. There's obliquity, which is the Earth's spin axis is not 90 degrees to the ecliptic plane. That's the plane that runs through all the planets, contains the sun, all 8 planets, including Earth. So the spin axis is not 90 degrees to that. It's at an angle. That's the obliquity angle. And that angle changes with a regular beat of 41,000 years. So it becomes more oblique, less oblique, more oblique, less oblique. And the last one is called precession. So if you think about a spinning top, and the spin axis of the top is moving around like this, that changes every 20,000 years. So those are the Milankovitch cycles. If you ever hear that word, that's what people are talking about. And they're important because they change climate. Some of them changes climate globally. Others just change it regionally, so making some parts of the Earth hotter and colder at various parts of the years. And if you look at the waxing and waning of ice sheets of the last 2.5 million years, they happen at beats of these Milankovitch cycles. And so the idea is that changes in the amount of radiation that's being felt, say, at a given patch of Earth or globally, are changing the ice sheet patterns and making them grow when it's colder, say, shrink when it's warmer. And so for Snowball Earth, there have been studies, there have been papers written who have actually argued for finding Milankovitch cyclicity in patterns of waxing and waning of snowball ice sheets. And so this is, again, but it's a much harder problem the further back in time you go. We've got very well-resolved records that study the last 2.5 million years. And there's no reason to think, as long as there's some, absent a total freeze, so the peak of Snowball Earth glaciation, but if ice sheets can grow and decay, then the expectation is that they would behave in response to those orbital forcing. So yeah, it's still very much a part of thinking about glaciations. One reason why you don't hear about it that much with Snowball Earth is, one, it may not have been applied in the depths of glaciation, And two, it's just much harder to find records that you can reliably say, oh, that's a change that's happening every 40,000 years. It's just too hard if you're talking about hundreds and hundreds of million-year-old rocks.
All right, let's take a question from this side. Yeah, thank you.
In the hypothesis, what would be the predicted temperature range between, say, Snowball Earth and CO2 saturation?
So what's the temperature range between Snowball Earth and CO2 saturation?
Ooh, I can't recall the number off my head. Paul can, though, at some point. Maybe he'll come up and give me the answer after the fact here. It's going to be below freezing during Snowball. That's a chicken answer to give you, but that's the best I could do at the moment. And then in terms of the aftermath, again, I don't know I have a number off the top of my head. I think 50 degrees Celsius is sticking in my head for some. These are all coming from climate models, predictions, right? But what I can tell you is that there's specialized measurements of geochemistry that people have done in the cap carbonates that formed in the aftermath of, you can kind of see it. It kind of works. That formed in the aftermath of these glacial meltdowns. And indications are that CO2 was as high as it's ever been in the last 800 million years in the aftermath of these glaciations. So that's another hypothesis that's being supported by again, observations. This evidence coming from a particular kind of geochemical measurement. So I think, the temperature, I can't quite recall. Again, that's coming from models, but I can tell you that there is evidence that CO2 has never been higher.
Right. Yeah, question here.
Yes, you've explained snow-covered Earth as an instability, albedo. However, we've had glaciations because of the Milankovitch hypothesis, which have created glaciers and quite a bit of snow-covered Earth, but not complete. So what prevents a glaciation, like 20,000 years ago or so, to becoming a ice-covered Earth?
What prevents regular glaciation becoming Snowball Earth?
Excellent question. So yes, it is definitely an instability. It's how you should think about it. Models are going to be different for when that instability kicks in. The earliest models, the ones where this ice albedo runaway were discovered, were probably too sensitive, in the sense that they were too easy to get to have runaway effects happen. But even in more sophisticated models, those instabilities exist. And so one idea actually goes back to the climate policeman. And so the idea is that if you're growing ice sheets in a colder temperature, what you're going to be doing as well as slowing down weathering rates. And that may have the effect of elevating or allow CO2 to remain elevated, which is going to act as a natural brake against those glaciations. And so it's a great question about why, why these Snowball Earth events are not as frequent as you may expect if it's something as simple as just making an ice sheet a little bit too big. One way that I like to think about it is that, Earth needs to have the right preconditions to make it sort of perched at these unstable points. And then probably what needs to happen is some kind of accident needs to occur. This is Paul's phrasing, I'm stealing it, but some kind of accident needs to happen that causes the Earth to cool too fast and kick in that runaway albedo effect to cause Earth to plunge into it. But otherwise, it seems like the natural feedbacks, the negative ones, are strong enough to resist these snowball states from happening that frequently. So yeah, I'll leave it there for right now.
Question from the red in the back there. Are there any other events that could stop erosion happening other than the Snowball Earth?
Yeah, no, I don't think so. I can't think of any, especially because one thing I haven't even talked about is the circulation of water through the seafloor, and that also has the ability of having chemical weathering happen and removing carbon from the ocean atmosphere system. So unless you truly freeze the Earth and cause those weathering reactions to stop or go very, very low, if you've got rock and if you've got water, those chemical reactions are going to happen. You can't really prevent them from occurring.
Yeah, question here.
What's the hypothesis for the future? Is global warming actually a good thing to keep us from going into another ice age?
So is global warming actually stopping us plunging into Snowball Earth again?
No. I can say more to that. Yeah, no, I don't want anyone to come away with the wrong idea. It's like, oh my God, all these people who want to reduce greenhouse gases are going to kill us all with the Snowball Earth. I think, again, this is the realm of natural processes that happen on a very different time scale from any kind of human processes. So, yeah, I don't think anyone, you shouldn't be worried about causing the Earth to get too cold by thinking about ways to reduce greenhouse gases.
Question at the back there.
Okay, one of the smartest people I've ever met is my neighbor, and he says there's one power source in the solar system, and that's the sun. And it has cycles. So where are we in solar cycles?
Where are we in solar cycles?
The number I know for solar cycles, I guess, is the sunspot cycle, and it happens every 10 years. I don't know where we are in terms of fluctuations in the sunspot cycle. I would say that it's not, you can't attribute climate change in the last, since the Industrial Revolution to anything like a natural cycle.
Okay, I'm going to take one more question right here.
I find it
Sorry.
interesting the discussion of energy in and energy out of the Earth. So on what scale does that exist? I mean, that's an Earth-centric sort of energy equation. So is that specific to where we are in the solar system? Does that exist in the solar system as a whole, or on a larger scale? Like, how does that scale work in the universe?
How universal is this energy balance idea?
Yeah, it's universal. It works for any planetary body that's receiving energy. It's going to emit that energy back out into space. So that's a sort of a universal observation from physics that this occurs.
Why can you not have like a runaway?
I think that it would just be, I'm stepping far outside my bounds here, but I think that it would just, it would explode. I mean, if you think about if the Earth's surface received more energy than it gives out, it wouldn't take long for it to completely melt down and not be a planet anymore. Certainly not a solid planet anymore. But, well, yeah, that comes from from stars and at the end of their lives. Yeah, but yeah.
Okay, maybe one more of your outstanding 29 questions.
So with respect to the glacial Earth and the origin of life, I think the most recent data is that the first evidence of life was about 3.2 billion years ago. And then the level of complexity increased throughout this time period. And the only thing special about what you referred to correctly as a Cambrian explosion was the occurrence of hard shell parts. It wasn't the diversity of groups. They existed already in the Precambrian. So anyway, could you just integrate that issue?
What can you tell us about shells?
It's good way to translate, Scott. Thank you. So certainly there's a long history of life that occurs in the Precambrian. So you have, for example, the oldest convincing microfossils, for people still argue about that, certainly by 2,800 million years ago. There are some fairly convincing microfossils. Certainly by the time you had oxygen in the atmosphere, you needed to have biology. If you talk about sort of the biology's role in influencing the environment, oxygen is an obvious answer. We didn't have oxygen without life, without photosynthesis. Eukaryotes evolve. That's and so you have eukaryotes, prokaryotes, and archaea throughout the Precambrian. I think it is definitely an open question how much bias we're introducing by saying, oh, we're observing all the different phyla of animal life. That scales with complexity. Is that true? Or is the actual sort of genetic machinery, in terms of developing all the genetic systems to allow complexity, that all happen when things were microbial, and the only thing that occurred is sort of this the appearance of life that appears to be what all the complexity is. Maybe all the complexity happened well before that, when things were still microscopic. I'm not a biologist, but I think that's a valid thing to think about for sure.
I know a lot of you are still busting to ask John questions. He will be here once we close it down, so please come up and chat to him. I need to talk about a couple of things because Nicole from the Dean's office gave me some pieces of paper from the Dean. The Dean couldn't be here tonight, so he's making me do his... The Dean is right here. Peter, would you like to come up and sell your argument then?
Oh, yeah, sure.
Okay.
Café Scientifique with a generous donation, or maybe not so generous donation. The event is free. We'd like to keep it this way, but we could certainly use your support. We're funding this out of our operating budget, which I could also spend on students. Just saying. It is a university after all, right? So students are part of the mix. So if you consider donating, some money, talk to me, or take that sheet. There's a QR code on it. Your cell phone can read it. It gets you to our website, and it's that simple to give us some money. And that's all I've got to say.
So I'd just like to second what Peter said. Like our speakers come along and do this for free. I'm hosting it for free as well. The main thing that costs us money is actually renting this fantastic venue, and we love having Café Sci down here at Herman's Jazz, and so this funding is what allows us to do that. One other thing is that if you really want to find out about some more science, in a month's time on May the 11th, we are hosting Science Rendezvous at UVIC. So if you're interested in that, please come along to UVIC. That's all free, lots of fun stuff. I will be doing something called Reaction Time. Lots of things from all the different departments happening at UVIC on that day. So we're done for Café Sci for the academic year. Please join me in thanking John and all the other speakers this year for a great talk.